Welcome to Tech with Kaushik. This is set 15 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam-ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 15. Now for question number 261. This one focuses on CI/CD pipelines. A DevOps engineer needs to integrate automated integration testing into an existing AWS code pipeline CI/CD workflow for an Amazon ECS service. The pipeline pulls code from code commit, builds a container image, and pushes it to Amazon EC/R with a new tag. The integration tests must verify that the updated service endpoints are reachable and that API methods return expected responses against a pre-created test ECS cluster. Which combination of steps will implement this integration testing stage with the least management overhead? Choose 3. Choose every option that satisfies the requirement. The choices are: Choice A, add a deployment stage to the pipeline using Amazon ECS as the direct action provider. Choice B, add a deployment stage to the pipeline using AWS Code Deploy as the action provider. Choice C, add an appspec.yml deployment specification file to the code commit repository. Choice D, update the build stage to output an image definitions.json file referencing the new image tag. Choice E, create an AWS Lambda function that executes connectivity checks and API validations against the service and integrate the Lambda function into code pipeline using a Lambda action stage. Choice F, write a standalone test script, upload it to an Amazon S3 bucket, and integrate the script into the pipeline using an S3 action stage. The required selections are option A, add a deployment stage to the pipeline using Amazon ECS as the direct action provider. Option D, update the build stage to output an image definitions.json file referencing the new image tag. And option E, create an AWS Lambda function that executes connectivity checks and API validations against the service and integrate the Lambda function into code pipeline using a Lambda action stage. Let's look at the reasoning. The scenario requires only a standard deployment into an already created test ECS cluster, not a code deploy blue/green deployment. The code pipeline Amazon ECS deploy action consumes image definitions.json to update the service to the newly built image. A Lambda invoke action can then run the endpoint and API validations and signal success or failure back to code pipeline with very little infrastructure to manage. The remaining options can be eliminated because B, code deploy is not required for a standard ECS deployment when no blue/green deployment behavior is requested. C, appspec.yml is associated with ECS to code deploy blue/green deployments and is not required for the standard ECS deploy action. F, an S3 action does not execute an arbitrary test script by itself. A compute action such as Lambda or code build is needed to run tests. Keep this point in mind for the exam. For code pipeline ECS deployments, standard ECS actions use image definitions.json. ECS blue/green actions use code deploy and an appspec file. Choose the simpler standard action when blue/green behavior is not required. Question number 262. Here's what is happening. An enterprise streams AWS network firewall flow logs into an Amazon S3 bucket for security analysis using Amazon Athena. Security governance mandates that these flow logs must be transformed and enriched with additional metadata before they land in the designated S3 bucket. Which solution meets these log transformation requirements with optimal architecture? Option A, create an AWS Lambda function with an S3 trigger on the bucket to transform data and write new objects, configuring recursive invocation protection. Option B, enable event bridge notifications on the S3 bucket, route events through a custom event bus to an AWS step functions workflow, and transform data into a secondary S3 bucket. Option C, configure an Amazon event bridge rule reacting to S3 object creation events with input transformations targeting a secondary S3 bucket. Option D, create an Amazon data firehose delivery stream configured with an AWS Lambda data transformer pointing to the S3 bucket as the destination and reroute network firewall logging to the firehose delivery stream. The best choice is option D. Create an Amazon Data Firehose delivery stream configured with an AWS Lambda data transformer pointing to the S3 bucket as the destination and reroute network firewall logging to the Firehose delivery stream. This is the best choice because Amazon Data Firehose integrates with AWS Lambda data transformation, so streaming records can be transformed and enriched before Firehose writes them to the destination S3 bucket. AWS Network Firewall can deliver supported logs to a Firehose delivery stream, avoiding post-delivery rewrite loops. Let's quickly check the incorrect choices. A. Transforming after the object lands in S3 does not satisfy the requirement that enrichment occur before landing in the designated bucket, and same bucket rewrites can create recursive event complexity. B. This transforms data only after S3 object creation and adds unnecessary orchestration for a streaming transformation requirement. C. Event bridge input transformers modify the event payload delivered to a target. They do not transform the underlying network firewall log records before S3 delivery. When streaming records must be transformed before S3 delivery, use Amazon Data Firehose with Lambda transformation rather than an S3 post-processing trigger. Here comes question number 263. Next, let's move into disaster recovery. Here's the scenario. An application runs on EC2 instances across multiple availability zones behind an application load balancer, ALB. Following a localized configuration error in one availability zone that caused a partial outage, a DevOps engineer needs to test traffic isolation by shifting ALB traffic away from the affected availability zone using Amazon Application Recovery Controller, ARC. Which solution enables this testing capability? Review the options. Option A. Enable zonal shift on the application load balancer and use Amazon Application Recovery Controller, ARC, to start a zonal shift away from the affected availability zone. Cross-zone load balancing can remain enabled. Option B. Disable cross-zone load balancing on the ALB target group and rely on target group health checks instead of enabling ARC zonal shift for the load balancer. Option C. Create Route 53 failover alias records for individual ALB nodes in each availability zone and use those DNS records as ARC zonal shift resources. Option D. Remove the affected subnet from the ALB before initiating a zonal shift, because ARC cannot shift an enabled ALB away from an availability zone while cross-zone load balancing is on. The right response is Option A. Enable zonal shift on the application load balancer and use Amazon Application Recovery Controller, ARC, to start a zonal shift away from the affected availability zone. Cross-zone load balancing can remain enabled. This works because zonal shift is disabled by default for an ALB and must be enabled before ARC can shift traffic away from an availability zone. Current ALB behavior supports zonal shift even when cross-zone load balancing remains enabled. ARC blocks traffic to targets in the shifted away zone and removes its zonal load balancer IP addresses from DNS. The other choices do not work because B. Target group health checks are not a substitute for the explicit ARC zonal shift test requested, and disabling cross-zone load balancing is not required. C. ARC zonal shift operates on supported zonal resources such as the ALB. It does not use per availability zone Route 53 alias records for individual ALB nodes. D. Removing an ALB subnet is not required to start a zonal shift, and current ARC/ALB behavior supports zonal shift with cross-zone load balancing enabled. Here's a useful exam tip. For ALB zonal shift, enable the ALB's ARC zonal shift integration first. Do not assume cross-zone load balancing must be disabled. Current ALB zonal shift supports it. Next up is question number 264. Consider this situation. A company defines its infrastructure using the AWS CDK within a CI/CD pipeline consisting of AWS Code Pipeline and AWS Code Build. The engineering team wants to introduce automated unit tests to validate infrastructure components during builds and ensure that deployments proceed only if all unit tests pass successfully. Which combination of steps will enforce this testing gate within the pipeline? Choose two. More than one answer may be correct. Here are the options. Choice A. Update the code build spec to execute unit tests before deployment and set the applicable build phase on failure setting to abort. Choice B. Update build spec commands to run unit tests and append the rollback true flag to the CDK deploy command. Choice C. Configure build spec commands to run tests and append the require approval any change flag to CDK deploy. Choice D. Create unit tests using the AWS CDK assertions module and use template has resource properties to verify expected resource properties. Choice E. Create a test script using CDK diff and fail the pipeline whenever any infrastructure change is detected. You should choose option A. Update the code build spec to execute unit tests before deployment and set the applicable build phase on failure setting to abort, and option D. Create unit tests using the AWS CDK assertions module and use template has resource properties to verify expected resource properties. The main reason is the AWS CDK assertions module supports fine-grained assertions against synthesized CloudFormation templates, including has resource properties. Running those unit tests in a code build phase before deployment and using the build spec on failure. Abort behavior ensures a failed test phase stops the build instead of allowing deployment to proceed. Now let's rule out the other options. B. Rollback controls deployment failure behavior. It does not make unit tests a required pre-deployment gate. C. The CDK approval flag introduces approval behavior rather than validating the infrastructure through automated unit tests. E. CDK diff reports infrastructure differences, but is not a substitute for unit assertions that verify required resource properties. A helpful shortcut is this. Use CDK assertions for infrastructure unit tests and run them before deployment in code build. The build spec key is on failure, and abort stops the build when that phase fails. Next up is question number 265. The focus now shifts to disaster recovery. Consider this situation. An application stores images in an Amazon S3 bucket, and a DevOps engineer is implementing a multi-region disaster recovery strategy to enable fast failover between S3 buckets in different regions. The business requires the AWS SLA-backed replication target that covers 99.99% of new objects within 15 minutes, and the team has already enabled two-way replication between the buckets. Which combination of additional steps should the DevOps engineer take to complete this architecture? Choose 3. Identify all valid responses. Here are the options. Choice A. Enable S3 replication time control, S3 RDC, on the replication rules for both S3 buckets. Choice B. Create an S3 multi-region access point configured in an active passive routing setup. Choice C. Invoke the submit multi-region access point routes operation via the AWS API when executing a failover to the secondary region. Choice D. Enable S3 transfer acceleration on both S3 buckets to optimize cross-region transfer speeds. Choice E. Configure a routing control in Amazon Route 53 application recovery controller and associate the S3 buckets in an active passive setup. Choice F. Invoke the update routing control states operation in the AWS API to initiate traffic failover to the secondary region S3 bucket. The answers that work here are option A. Enable S3 replication time control, S3 RDC, on the replication rules for both S3 buckets. Option B. Create an S3 multi-region access point configured in an active passive routing setup. And option C. Invoke the submit multi-region access point routes operation via the AWS API when executing a failover to the secondary region. S3 replication time control provides the SLA-backed target of replicating 99.99% of new objects within 15 minutes. S3 multi-region access points provide a global S3 access endpoint with failover controls, and submit multi-region access point routes changes bucket routing between active and passive regions during a failover. D. S3 transfer acceleration optimizes client transfers to S3. It does not provide the S3 replication time, SLA, or multi-region access point failover routing. E. S3 multi-region access point failover uses S3's native failover control routing rather than ARC routing controls for the buckets. F. Update routing control states is an ARC routing control API, not the API used to change S3 multi-region access point routes. Exam tip. S3 RDC is an SLA-backed replication feature for 99.99% of new objects within 15 minutes. Pair it with multi-region access point failover controls when the access path must switch regions quickly. Now for question number 266. Here's the scenario. An organization utilizing AWS organizations with all features enabled configures AWS backup in a primary account using an AWS KMS key for backup encryption. To establish automated cross-account backups, the team creates a new member account, provisions a backup vault and a dedicated KMS key in that new account, and configures a backup plan in the primary account targeting the new account's vault. Although backup jobs successfully create recovery points in the primary account, copies fail to transfer to the new account's vault. Which combination of steps must the company take to enable successful cross-account backup copies? Choose 2. Select all answers that apply. Review the options. Option A. Edit the backup vault access policy in the destination member account to grant backup copy permissions to the primary account. Option B. Edit the backup vault access policy in the primary account to authorize access from the new member account. Option C. Modify the primary account backup vault access policy to allow access to the destination KMS key. Option D. Update the KMS key policy in the primary account to share the encryption key with the new member account. Option E. Update the KMS key policy in the destination member account to grant decryption and encryption permissions to the primary account. The correct answers are Option A. Edit the backup vault access policy in the destination member account to grant backup copy permissions to the primary account, and Option D. Update the KMS key policy in the primary account to share the encryption key with the new member account. Here's why. For a cross-account copy, the destination backup vault must allow backup copy into backup vault from the source account or role. When the source backups are protected with a customer-managed KMS key, that source key must also be shared with the destination account, so AWS backup can copy the encrypted recovery point. AWS backup then re-encrypts the copy with the destination vault key. Here's why the alternatives are not suitable. B. The destination vault resource policy, not the source vault policy, controls whether a cross-account copy can be written into the destination vault. C. A source backup vault policy does not grant KMS permissions for the destination key. E. The destination key is used by AWS backup in the destination account to encrypt the copied recovery point. The cross-account key sharing requirement in this scenario applies to the source customer-managed key that protects the source backup. The main takeaway is for AWS backup cross-account copies, authorize backup, copy into backup vault on the destination vault, and share the source customer-managed KMS key when the source recovery point is encrypted with that key. The copy is re-encrypted with the destination vault key. Here comes question number 267. A DevOps team uses Amazon EC2 as its primary compute platform and needs to audit all EC2 instances across the fleet to detect whether any unauthorized or prohibited software applications have been installed. Which solution satisfies this requirement with the highest operational efficiency? The choices are: Choice A. Configure AWS Systems Manager on each instance. Enable Systems Manager inventory. Export inventory data to S3 via Resource Data Sync, and process objects with an AWS Lambda function to flag prohibited applications. Choice B. Configure AWS Systems Manager on each instance. Enable Systems Manager inventory, and create AWS config rules monitoring inventory changes to identify prohibited applications. Choice C. Configure Systems Manager on each instance. Enable inventory collection, and filter AWS CloudTrail logs for Systems Manager Inventory API events to detect unauthorized software. Choice D. Stream application instance logs to Amazon CloudWatch logs. Execute custom inventory scripts across instances, and create CloudWatch alarms with filter patterns searching for prohibited applications. The answer here is Option B. Configure AWS Systems Manager on each instance. Enable Systems Manager inventory, and create AWS config rules monitoring inventory changes to identify prohibited applications. Let's look at the reasoning. Systems Manager inventory collects installed software data from EC2 instances. Integrating Systems Manager inventory with AWS config enables continuous compliance monitoring and rule evaluation to detect prohibited applications with maximum operational efficiency and minimal custom code. The remaining options can be eliminated because A. Exporting inventory data to S3 and writing custom Lambda functions introduces unnecessary development overhead compared to native AWS config integration. C. CloudTrail captures API events, not guest operating system installed software inventory. D. Streaming logs to CloudWatch and parsing custom scripts requires complex log filtering and custom log agents, lacking operational efficiency. Keep this point in mind for the exam. To audit installed software across EC2 fleets with high operational efficiency, use Systems Manager Inventory combined with AWS config rules. Question number 268. We're moving on to disaster recovery. Here's what is happening. An enterprise is deploying an application backend across a secondary AWS region. The application uses Amazon DynamoDB tables and Amazon S3 buckets. Business continuity requirements state that new data must be replicated automatically across both regions with low latency and minimal custom operational code so that either region has a current copy for recovery. Which architectural solution meets these requirements with the highest operational efficiency? Option A. Implement two-way S3 replication between the primary and secondary region buckets, and convert the DynamoDB tables to global tables by adding a replica in the secondary region. Option B. Implement scheduled S3 batch replication jobs between regions and configure DynamoDB global tables for the tables. Option C. Configure two-way S3 replication and implement custom Lambda functions on DynamoDB streams in both regions to replicate table updates. Option D. Use scheduled S3 batch operations copy jobs and custom Lambda functions subscribed to DynamoDB streams to replicate table records across regions. In this case, choose option A. Implement two-way S3 replication between the primary and secondary region buckets, and convert the DynamoDB tables to global tables by adding a replica in the secondary region. This is the best choice because Amazon S3 Live Replication can replicate new objects automatically across regions, and two-way replication supports writes in either bucket when configured in both directions. DynamoDB global tables provide fully managed multi-region replication and can serve reads and writes from replicas, avoiding custom DynamoDB streams and Lambda replication code. Let's quickly check the incorrect choices. B. Batch replication is an on-demand or scheduled mechanism and is less suitable than live replication for automatic low-latency propagation of new S3 objects. C. Custom stream processing Lambda functions add operational complexity when DynamoDB global tables already provide managed multi-region replication. D. Both S3 batch copies and custom DynamoDB stream replication add operational overhead and do not provide the simplest managed low-latency architecture. S3 Live Replication and DynamoDB global tables are managed multi-region replication mechanisms. Do not describe ordinary S3 replication as instantaneous. It is asynchronous unless a specific replication time, SLA such as S3RDC, is required. Question number 269. Here's the scenario. A DevOps team configures Amazon RDS storage autoscaling for production database instances. The engineering team needs to visualize RDS storage autoscaling events on an Amazon CloudWatch operational dashboard. Which solution fulfills this visualization requirement? Here are the options. Choice A. Create an Amazon Event Bridge rule reacting to RDS storage autoscaling events from RDS service events. Configure an AWS Lambda function to publish a CloudWatch custom metric, and visualize the custom metric on the CloudWatch dashboard. Choice B. Create an AWS CloudTrail trail capturing management events, stream events to CloudWatch logs. Create a metric filter matching storage autoscaling events, and visualize the metric filter on the dashboard. Choice C. Configure an Event Bridge rule to react to RDS storage autoscaling events, update a CloudWatch alarm state, and track the alarm status on the CloudWatch dashboard. Choice D. Create a CloudTrail trail capturing data events, stream events to CloudWatch logs. Create a log metric filter for autoscaling events, and visualize the metric on the dashboard. Go with option A. Create an Amazon Event Bridge rule reacting to RDS storage autoscaling events from RDS service events. Configure an AWS Lambda function to publish a CloudWatch custom metric, and visualize the custom metric on the CloudWatch dashboard. This works because Amazon RDS storage autoscaling events are emitted as Event Bridge events from RDS. Because standard CloudWatch metrics do not natively expose a direct countermetric for storage autoscaling events, capturing the event via Event Bridge and invoking a Lambda function to publish a custom CloudWatch metric allows seamless visualization on a CloudWatch dashboard. The other choices do not work because B. CloudTrail management events sent to CloudWatch logs and metric filters capture API calls, but our DS storage autoscaling execution events are emitted natively by our DS event notifications, not IAM/management API trails. C. Changing CloudWatch alarm states via Event Bridge does not generate a continuous time series metric suitable for standard dashboard visualization. D. Our DS storage events are management/service events, not S3-style data events. Here's a useful exam tip. To visualize operational service events, such as our DS storage autoscaling, on CloudWatch dashboards, capture the events with Event Bridge and publish custom metrics via AWS Lambda. Now for question number 270. This question takes us into IAM at scale. Here's what is happening. A company is deploying a data processing workload across several hundred Amazon EC2 instances managed in an auto-scaling group using a launch template. The workload pulls raw data files from an S3 bucket, processes them, and writes results to a separate S3 bucket. The instances must adhere to strict least privilege security principles and utilize temporary security credentials rather than long-term static access keys. Which combination of steps will satisfy these security requirements? Choose 2. Select all answers that apply. The choices are: Option A. Create an IAM role with least privilege permissions scoped to the required S3 buckets and attach the role to an instance profile. Option B. Update the EC2 launch template to include the IAM instance profile. Option C. Create an IAM user with specific S3 permissions and generate static access keys and security tokens. Option D. Establish an IAM trust anchor and mapping profile and attach the IAM execution role to the profile. Option E. Modify the EC2 user data script in the launch template to inject the static access keys and tokens at startup. The required selections are Option A. Create an IAM role with least privilege permissions scoped to the required S3 buckets and attach the role to an instance profile, and Option B. Update the EC2 launch template to include the IAM instance profile. The main reason is to provide EC2 instances with temporary security credentials and least privilege access to S3 without using static credentials. An IAM role must be created and added to an instance profile. Referencing this instance profile in the EC2 launch template ensures all instances launched in the auto-scaling group automatically inherit the correct secure permissions. Now let's rule out the other options. C. IAM users and static access keys violate security best practices and least privilege requirements for automated EC2 fleets. D. IAM trust anchors and profiles are used for IAM roles anywhere, hybrid/on-premises workloads, not standard EC2 instance profiles. E. Injecting static credentials into user data exposes sensitive keys and violates temporary credential requirements. A helpful shortcut is this. Always use IAM roles and instance profiles referenced in launch templates to grant EC2 instances temporary security credentials and least privilege access. Next up is question number 271. Consider this situation. A DevOps team manages container images stored in Amazon Elastic Container Registry, Amazon ECR, that are deployed to a AWS app runner. The team requires a solution to continuously monitor the repository. If an operating system or programming language package vulnerability is detected, the solution must automatically trigger the creation of a patched container image. Which solution satisfies these requirements with the least operational overhead? Choice A. Enable Amazon Guard Duty malware protection on the App Runner service. Create an Amazon Event Bridge rule that captures Guard Duty finding events and triggers an EC2 image builder pipeline. Choice B. Turn on Amazon ECR basic scanning. Create an AWS code build project. Configure an Amazon Event Bridge rule that captures ECR image action events and triggers the code build project. Choice C. Turn on Amazon ECR enhanced scanning. Create an EC2 image builder container pipeline. Configure an Amazon Event Bridge rule that captures Amazon Inspector finding events and triggers the image builder pipeline. Choice D. Use AWS Systems Manager compliance to scan the containers. Create an AWS code build project. Configure an Amazon Event Bridge rule that captures compliance state changes and triggers the code build project. Go with option C. Turn on Amazon EC or enhanced scanning. Create an EC2 image builder container pipeline. Configure an Amazon Event Bridge rule that captures Amazon Inspector finding events and triggers the image builder pipeline. Amazon EC or enhanced scanning integrates with Amazon Inspector and supports continuous scanning for operating system and programming language package vulnerabilities. Amazon Inspector findings can be delivered through Amazon Event Bridge, which can start an EC2 image builder container pipeline that is configured to rebuild and publish the patched image. This satisfies both the continuous vulnerability monitoring requirement and the automated remediation workflow with managed AWS services. A. Guard Duty Malware Protection is not the EC or package vulnerability scanning service required by the scenario. B. Amazon EC or basic scanning uses AWS native scanning for operating system vulnerabilities, but it does not provide the programming language package coverage required here. D. Systems Manager Compliance evaluates managed node patch and configuration compliance. It is not the native service for continuously scanning images stored in EC or for both OS and language package vulnerabilities. Exam tip. EC or enhanced scanning is integrated with Amazon Inspector and adds continuous scanning plus programming language package vulnerability coverage. Current EC or basic scanning is AWS native and focuses on operating system vulnerabilities. Here comes question number 272. A company is developing a new application in a dedicated AWS organization's member account. A developer needs the ability to create and remove service-linked IAM roles required for testing selected AWS services. A DevOps engineer must grant only the IAM permissions needed for service-linked role lifecycle operations and must not grant full IAM administrative permissions. Which solution meets these security requirements with the least privilege? Review the options. Option A. Attach a service control policy, SCP, to the member account that explicitly denies all IAM * actions except IAM. Create service-linked role. Option B. Grant the developer an IAM role whose policy allows IAM. Create service-linked role, IAM. Delete service-linked role, and IAM. Get service-linked role deletion status, and restrict IAM. Create service-linked role to the required services by using the IAM. AWS service name condition key, where applicable. Option C. Create an IAM user for the developer in the AWS organization's management account and grant cross-account access limited to IAM service-linked role creation. Option D. Assign the developer to an IAM group with the AWS Managed Power User Access Policy and require multi-factor authentication, MFA. The best choice is option B. Grant the developer an IAM role whose policy allows IAM. Create service-linked role, IAM. Delete service-linked role, and IAM. Get service-linked role deletion status, and restrict IAM. Create service-linked role to the required services by using the IAM. AWS service name condition key, where applicable. Here's why. Service-linked roles are predefined by the AWS service that owns them. The least privilege approach is therefore to grant only the IAM actions required to create and remove service-linked roles and, when possible, constrain creation to the required AWS service names. This gives the developer the requested capability without broad IAM administration. Here's why the alternatives are not suitable. A. An SCP sets the maximum available permissions for principals in an account. It does not itself grant the developer the required IAM permissions. A broad account-level deny would also affect unrelated principals and IAM operations. C. Day-to-day workload administration should not be moved into the organization's management account merely to delegate service-linked role permissions. D. Power user access is substantially broader than the requested service-linked role lifecycle permissions and therefore violates least privilege. The main takeaway is for service-linked roles, grant the specific IAM. Create service-linked role and lifecycle permissions that are required. Use IAM, AWS service name, to scope creation to selected AWS services when the action supports that condition. Here comes question number 273. Next, let's move into CI/CD pipeline observability. Here's the scenario. A company uses AWS Code Pipeline, AWS Code Build, and AWS Code Deploy for its microservices CI/CD pipelines. The engineering team wants to track lead time for changes and mean time to recovery, MTTR, by analyzing the time elapsed between successful and failed pipeline executions. Which solution provides this pipeline visibility with the least operational overhead? Here are the options. Option A. Create an AWS Lambda function that extracts pipeline run metrics and publishes them as custom Amazon CloudWatch metrics. Configure an Amazon Event Bridge rule to invoke the Lambda function every 5 minutes. Option B. Create an AWS Lambda function that writes pipeline execution state data to Amazon DynamoDB. Configure an Amazon Event Bridge rule to invoke the Lambda function after every successful and failed pipeline run. Build an Amazon QuickSight dashboard. Option C. Create an AWS Lambda function that extracts pipeline run metrics and publishes them as custom Amazon CloudWatch metrics. Configure an Amazon Event Bridge rule to invoke the Lambda function whenever a pipeline execution state changes to succeeded or failed. Option D. Schedule an Amazon Event Bridge rule to invoke an AWS Lambda function every 5 minutes. Configure the Lambda function to query the AWS Code Pipeline API, store the results in Amazon DynamoDB, and visualize with Amazon QuickSight. The right response is option C. Create an AWS Lambda function that extracts pipeline run metrics and publishes them as custom Amazon CloudWatch metrics. Configure an Amazon Event Bridge rule to invoke the Lambda function whenever a pipeline execution state changes to succeeded or failed. Let's look at the reasoning. AWS Code Pipeline natively emits state change events, such as Code Pipeline execution state change, to Amazon Event Bridge. Triggering a Lambda function asynchronously based on these events is a scalable, event-driven approach. The Lambda function can calculate the execution duration and publish it as a custom CloudWatch metric, which can then be easily visualized on CloudWatch dashboards. The remaining options can be eliminated because A. Polling a pipeline status every 5 minutes creates unnecessary overhead, API throttling risks, and introduces reporting delays compared to event-driven processing. B. While DynamoDB and QuickSight can work, building and maintaining a BI dashboard for basic MTT or /lead time metrics requires more operational effort than publishing custom metrics to CloudWatch, which provides native dashboarding. D. Polling via Event Bridge every 5 minutes and managing a QuickSight dashboard combines the inefficiency of polling with the overhead of managing a separate BI tool. Keep this point in mind for the exam. Prefer event-driven architectures, Event Bridge triggering Lambda on state changes, over scheduled polling loops for CI/CD observability. Question number 274. Let's go. A company is adding automated security checks to its AWS Code Pipeline CI/CD workflow. The pipeline builds a container image, pushes it to an Amazon Elastic Container Registry, Amazon ECR, repository, and then deploys the image. A DevOps engineer must ensure the pipeline fails and blocks deployment if the image contains any critical or high vulnerabilities in either the operating system or programming language packages. Which combination of steps should the DevOps engineer take to meet these requirements? Choose 2. Identify all valid responses. Option A. Enable Amazon ECR enhanced scanning on the repository. Option B. Enable Amazon ECR basic scanning on the repository. Option C. Configure the ECR repository itself to return a failed code pipeline action whenever an image contains critical or high findings. Option D. Add a code build security gate action after the image push. Configure the build to wait for the enhanced scan result, evaluate the Amazon inspector findings, and exit with a non-zero status when any critical or high finding is present. Option E. Add a code build security gate action after the image push that evaluates only ECR basic scanning findings and exits with a non-zero status when any critical or high finding is present. You should choose Option A. Enable Amazon ECR enhanced scanning on the repository, and Option D. Add a code build security gate action after the image push. Configure the build to wait for the enhanced scan result, evaluate the Amazon inspector findings, and exit with a non-zero status when any critical or high finding is present. This is the best choice because ECR enhanced scanning integrates with Amazon Inspector and covers both operating system and programming language package vulnerabilities. A code build action can act as an explicit pipeline gate by waiting for the scan result, evaluating the severities, and returning a failed build when a high or critical finding exists. A failed code build action stops the pipeline before the deployment stage. Let's quickly check the incorrect choices. B. Current ECR basic scanning focuses on operating system vulnerabilities and does not satisfy the requirement to assess programming language packages. C. An EC or repository does not directly return a success or failure result to a code pipeline action based on vulnerability severity. The pipeline needs an action or integration that evaluates findings and fails the workflow. A gate that relies only on basic scanning findings cannot satisfy the programming language package vulnerability requirement. Use EC or enhanced scanning with Amazon Inspector when a container security gate must cover both OS and programming language packages. Make the CI/CD pipeline explicitly fail when findings exceed the allowed severity threshold. Question number 275. A company uses AWS organizations and deploys all infrastructure, including IAM policies and Amazon S3 buckets, through AWS CloudFormation template stored in AWS code commit. Recently, developers in specific organizational units, OUs, reported that they can no longer access a centralized S3 bucket. The bucket policy grants access to a specific developer IAM role. What is the most appropriate way for a DevOps engineer to restore access while adhering to the company's deployment practices? The choices are: Choice A. Disable S3 block public access on the bucket through the AWS Management Console. Add an AWS source account condition to the bucket policy containing the affected account IDs. Choice B. Determine whether SCPs attached to the affected OUs or permissions boundaries attached to the developer roles are denying the required S3 actions. Correct the applicable policy definitions in code commit and deploy the change through the organization's CloudFormation-based infrastructure as code process. Choice C. Use AWS config remediation to revert IAM permissions boundary changes in the affected accounts. Update the S3 bucket policy directly to include an AWS source account condition. Choice D. Create a new SCP that prevents modification of IAM resources in the affected OUs and deploy it through CloudFormation. The answer here is option B. Determine whether SCPs attached to the affected OUs or permissions boundaries attached to the developer roles are denying the required S3 actions. Correct the applicable policy definitions in code commit and deploy the change through the organization's CloudFormation-based infrastructure as code process. This works because a resource-based S3 bucket policy cannot override an explicit deny imposed by an applicable SCP or IAM permissions boundary. Because only accounts in particular OUs are affected, those organization or principal-level guardrails are strong candidates for the denial. The company also requires infrastructure changes to follow its version-controlled CloudFormation process, so the appropriate remediation is to correct the governing policy as code and redeploy it. The other choices do not work because A. Disabling block public access is unrelated to restoring authenticated cross-account access, and a manual console change violates the stated infrastructure as code process. An AWS source account condition also cannot override an explicit deny. C. Reverting policy state outside the authoritative infrastructure as code workflow can create drift, and changing the bucket policy does not overcome an explicit deny in an applicable SCP or permissions boundary. D. Adding another restrictive SCP does not restore the missing S3 permissions and can make the access problem worse. Here's a useful exam tip. When an organization uses infrastructure as code as the source of truth, diagnose the full authorization path first, including SCPs and permissions boundaries. Then repair the authoritative policy definition and redeploy it through the established infrastructure as code workflow. Next up is question number 276. The focus now shifts to code artifact architecture. Consider this situation. A DevOps engineer is designing an AWS code artifact strategy for a multi-account AWS organization's environment. Each application team operates in its own AWS account and needs to publish and download its own software packages. The organization also maintains shared library packages in a centralized shared services account. Each team should consume the shared libraries through its own repository, and the design should minimize the number of code artifact domains. Which combination of steps will meet these package management requirements with the least administrative overhead? Choose 4. Choose every option that satisfies the requirement. Option A. Create one AWS code artifact domain in the shared services account and configure the domain resource policy to permit the required cross-account domain access for the application accounts. Option B. Create a separate AWS code artifact domain in each application team's account. Option C. Create a shared repository in the shared services account and grant the application accounts the repository permissions required to read the shared packages and associate the repository as an upstream repository. Option D. Create an application-specific repository in each application team's account within the centrally owned domain, and grant the respective team read and publish permissions for its repository. Option E. Set the application team's repositories as upstream repositories for the shared services repository. Option F. Set the shared services repository as an upstream repository for each application team's repository. The correct answers are Option A. Create one AWS code artifact domain in the shared services account and configure the domain resource policy to permit the required cross-account domain access for the application accounts. Option C. Create a shared repository in the shared services account and grant the application accounts the repository permissions required to read the shared packages and associate the repository as an upstream repository. Option D. Create an application-specific repository in each application team's account within the centrally owned domain and grant the respective team read and publish permissions for its repository. And Option F. Set the shared services repository as an upstream repository for each application team's repository. The main reason is code artifact upstream and downstream repositories must be in the same domain, so a single centrally owned domain minimizes administration and permits shared dependency resolution across accounts. Cross-account use of the central domain requires appropriate domain permissions, and cross-account access to repositories requires the corresponding repository permissions. Each team can own and administer its application repository while associating it with the central domain. Making the shared repository upstream of each team repository lets package managers resolve shared libraries through the team's normal repository endpoint. Now let's rule out the other options. B. Separate domains prevent the repositories from participating in the same native upstream/downstream graph and increase administrative overhead. E. This reverses the desired dependency direction. Team repositories need to consume shared libraries, so the shared repository should be upstream of the team repositories. A helpful shortcut is this. Code artifact upstream relationships stay within one domain. For multi-account designs, centralize the domain, use resource policies for cross-account access, and point team repositories upstream to the shared dependency repository. Now for question number 277. Here's what is happening. An application processes data records through a sequential, compute-intensive pipeline. Currently, the processing is managed by a custom application running on a single Amazon EC2 instance. Each processing step takes up to 4 minutes. If any step fails, the custom application reruns the entire sequence from the beginning, causing significant delays. A DevOps engineer must redesign the architecture so that if a step fails, only the failed step is retried. Which solution is the most operationally efficient way to meet these requirements? Review the options. Choice A. Decouple the sequential steps using an Amazon Kinesis data stream and multiple AWS Lambda functions. Choice B. Refactor the application to write intermediate state to Amazon S3. Use S3 event notifications to trigger Amazon EC2 instances via Amazon SNS. Choice C. Orchestrate the pipeline using AWS step functions, decoupling the processing into individual tasks executed by AWS Lambda functions. Choice D. Containerize the application and run it on AWS Fargate. Configure the container to invoke itself recursively to pass state between steps. In this case, choose option C. Orchestrate the pipeline using AWS step functions, decoupling the processing into individual tasks executed by AWS Lambda functions. AWS Step Functions is a serverless orchestration service specifically designed to manage multi-step, sequential workflows. It natively handles state transitions, errors, and retries at the individual step level. By decoupling the 4-minute compute tasks into AWS Lambda functions, which have a 15-minute execution limit, Step Functions ensures that if Step 3 fails, only Step 3 is retried, satisfying the requirement with minimal operational overhead. A. Kinesis is designed for streaming data, not for orchestrating sequential stateful workflows with step-level error handling. Building a state machine with Kinesis and Lambda requires significant custom code. B. S3 event notifications triggering EC2 instances is a loosely coupled asynchronous pattern, but it lacks built-in state management and automated step-level retries without complex custom logic. D. While Fargate can run containers, having a container recursively invoke itself to pass state is an anti-pattern that creates brittle, difficult-to-monitor code compared to a managed state machine. Exam tip. Whenever a scenario requires orchestrating sequential steps, managing state, handling failures gracefully, and retrying specific failed tasks, AWS step functions is the intended solution. Question number 278. This question takes us into centralized logging. Here's what is happening. A company uses AWS organizations and must consolidate Amazon CloudWatch logs from all current and future member accounts into an Amazon S3 bucket in a centralized security account. Newly created log groups must be included automatically, and the solution should minimize per-account automation. Which solution meets these requirements with the least operational overhead? Review the options. Option A. Configure a CloudWatch logs centralization rule for the organization that replicates matching log data to the security account. In the security account, configure an account-level CloudWatch logs subscription filter for the centralized log groups that sends the events to an Amazon Data Firehose delivery stream whose destination is the S3 bucket. Option B. Use AWS Backup to create a backup plan for CloudWatch logs and specify the S3 bucket as the backup vault. Use AWS config remediation to attach new log groups to the backup plan. Option C. Configure an AWS organization's backup policy to backup every CloudWatch log group directly to the S3 bucket. Option D. In every member account, manually create and maintain log group level subscription filters that send events to a separate Amazon Data Firehose delivery stream in that account, with all streams writing to the central S3 bucket. The right response is Option A. Configure a CloudWatch logs centralization rule for the organization that replicates matching log data to the security account. In the security account, configure an account-level CloudWatch logs subscription filter for the centralized log groups that sends the events to an Amazon Data Firehose delivery stream whose destination is the S3 bucket. Here's why. CloudWatch logs centralization integrates with AWS organizations and can automatically replicate new log data from matching source accounts and log groups into a centralized destination account. After centralization is enabled, subscription filters can be applied to the centralized logs. An account-level subscription filter in the security account avoids per-log group automation and can continuously forward the centralized events to Amazon Data Firehose for delivery to S3. Here's why the alternatives are not suitable. B. AWS Backup stores supported backups in backup vaults. It is not the mechanism for streaming CloudWatch log events into a normal S3 analytics bucket. C. Organizations' backup policies do not turn an S3 bucket into an AWS backup vault and do not provide continuous CloudWatch logs delivery to S3. D. Per account, per log group subscription management, and separate delivery streams create substantially more administration and do not automatically solve future account governance as cleanly as organizations' integrated log centralization. The main takeaway is in current multi-account environments, prefer CloudWatch logs centralization for organization-wide log replication. Then apply centralized subscription or account-level filters for downstream delivery and processing. Question number 279. Scenario. A company manages its AWS accounts using AWS organizations. Access is provisioned via AWS IAM Identity Center in the management account. The DevOps team is assigned a permission set named DevOpsAdmin that grants administrator access across all member accounts. The security team wants to explicitly prevent the DevOps team from modifying IAM Identity Center configurations in the management account. The security team applied a service control policy, SCP, at the organization root denying SSO asterisk and SSO directory asterisk for the DevOps IAM role. However, the DevOps team can still modify IAM Identity Center settings. Which solution will successfully restrict the DevOps team's access in the management account? Options. Option A. Move the organization's management account into a newly created organizational unit, OU, and attach the SCP directly to the new OU instead of the root. Option B. Update the SCP condition to explicitly include the management account's AWS account ID in the AWS principal ARN condition key. Option C. Create a new permission set in IAM Identity Center that provides administrator access, but explicitly denies SSO asterisk and SSO directory asterisk. Assign this new permission set to the DevOps group exclusively for the management account, and remove the ineffective SCP. Option D. Update the existing DevOps admin permission set with an inline policy that explicitly denies SSO asterisk and SSO directory asterisk when the AWS source account matches the management account ID. Go with option C. Create a new permission set in IAM Identity Center that provides administrator access, but explicitly denies SSO asterisk and SSO directory asterisk. Assign this new permission set to the DevOps group exclusively for the management account, and remove the ineffective SCP. Let's look at the reasoning. Service control policies, SCPs, do not affect the management account of an organization. They only restrict member accounts. Therefore, applying an SCP to the root will not prevent the DevOps team from accessing IAM Identity Center inside the management account. The correct way to implement this restriction is to create a modified permission set in IAM Identity Center that contains the explicit deny statements and assign this restrictive permission set to the DevOps group specifically on the management account. The remaining options can be eliminated because A. The AWS organization's management account always resides at the root and cannot be moved into an organizational unit, OU. B. SCPs simply do not apply to the management account, regardless of how the condition keys are configured. D. Updating the global DevOps admin permission set with conditional logic based on account ID is functionally possible, but unnecessarily complex and fragile compared to mapping a specific restrictive permission set strictly to the management account. Keep this point in mind for the exam. SCPs never restrict the management account. To restrict access in the management account, you must manage the identity's native IAM policies or IAM Identity Center permission sets. Here comes question number 280. Here's the scenario. A company's AWS organization structure includes an organizational unit, OU, named production, which contains a child OU named backend. Both OUs currently have the default full AWS Access Service Control Policy, SCP, attached. Member accounts within the backend OU contain IAM roles with the Administrator Access Managed policy attached. A DevOps engineer detaches the full AWS Access SCP from the production OU and replaces it with an SCP that contains only an allow statement for EC2 asterisk actions. What is the resulting effective permission for the IAM roles in the backend member accounts? Choice A. The roles will be able to perform all API actions on all AWS resources because they have the Administrator Access policy attached. Choice B. The roles will be able to perform all API actions on all AWS resources because the backend OU still has the full AWS Access SCP attached. Choice C. The roles will be able to perform only Amazon EC2 API actions. All other AWS API actions will be implicitly denied. Choice D. The roles will be completely denied from performing any AWS API actions because the custom SCP does not explicitly allow IAM permissions. The best choice is option C. The roles will be able to perform only Amazon EC2 API actions. All other AWS API actions will be implicitly denied. This is the best choice because in AWS organizations, effective permissions are the intersection of service control policies, SCPs, at every level, root, OU, child OU, and the principal's IAM policy. If the production OU has an SCP that only allows EC2 asterisk, it implicitly denies all other services. Because backend is a child of production, it inherits this restriction. Thus, even though the IAM role has administrator access, the SCP acts as a hard ceiling, limiting them entirely to EC2 actions. Let's quickly check the incorrect choices. A. IAM permissions never override an implicit or explicit deny from an SCP in the inheritance path. B. Although the backend OU has full AWS access, the parent production OU restricted access to EC2 only. SCP inheritance strictly filters permissions down the tree. D. An SCP does not need to explicitly allow IAM asterisk unless the user requires IAM permissions. The prompt asks what the roles can do, which is EC2 actions. SCPs do not grant permissions. They act as a filter. A missing allow in an SCP anywhere in the hierarchy results in an implicit deny for that service, regardless of the user's IAM policy. Next up is question number 281. We're moving on to configuration management. A DevOps engineer manages an Amazon EC2 auto-scaling group. Instances are launched using an AMI that includes the AWS Systems Manager agent. The auto-scaling group automatically applies specific tags to the instances it launches. The engineer must ensure that a desired baseline operating system configuration is automatically applied to these instances as soon as they launch. Which solution will meet these requirements with the least manual intervention? Here are the options. Choice A. Create an AWS Systems Manager patch group using the auto-scaling group tags. Register the group with a patch baseline that runs a command document. Choice B. Create an AWS Systems Manager State Manager association that executes a configuration command document. Configure the association to target instances based on the tags applied by the auto-scaling group. Choice C. Create an AWS Systems Manager run command task specifying the desired configuration. Schedule a daily Systems Manager maintenance window to execute the task on the tagged instances. Choice D. Configure AWS Systems Manager compliance to monitor the tagged instances. Create an Amazon Event Bridge rule that triggers a Systems Manager run command document when an instance is reported as non-compliant. The answer here is option B. Create an AWS Systems Manager State Manager association that executes a configuration command document. Configure the association to target instances based on the tags applied by the auto-scaling group. This works because AWS Systems Manager State Manager is the service designed to maintain consistent configuration, desired state, across Amazon EC2 instances. By creating a State Manager association targeted by resource tags, State Manager will automatically detect when the auto-scaling group launches a new instance with those tags and immediately apply the specified configuration document, requiring zero manual intervention. The other choices do not work because A. Patch Manager is designed for applying OS updates and patches, not for general baseline OS configuration bootstrapping. C. A run command task scheduled via a maintenance window will only execute at the scheduled time, for example, daily. Instances launched between windows would remain unconfigured until the next run. D. Event Bridge triggering run command based on compliance state is complex and slower than using State Manager, which is purpose-built for desired state enforcement upon instance launch. Here's a useful exam tip. For continuous, automatic enforcement of OS configurations on dynamic ASG fleets, use AWS Systems Manager State Manager targeted by tags. Now for question number 282. Consider this situation. A company hosts a web application on Amazon Elastic Container Service, Amazon ECS, behind an application load balancer, ALB. The application was stable until a DevOps engineer deployed a new task definition containing an updated container image. Following the deployment, the ECS service continually starts new tasks, which are subsequently stopped after a short period because they fail the ALB health checks. The new container image takes significantly longer to initialize than the previous version. What is the most appropriate configuration change to stabilize the deployment? The choices are: Option A. Decrease the health check interval on the ALB target group so it can detect the application's readiness faster. Option B. Verify the security group attached to the ECS service allows inbound traffic from the ALB. Option C. Increase the minimum healthy percent parameter in the ECS service deployment configuration. Option D. Increase the health check grace period on the ECS service configuration. In this case, choose option D. Increase the health check grace period on the ECS service configuration. The main reason is when an ECS task sits behind an ALB, ECS registers the task with the ALB target group. If the application takes a long time to start up, for example, loading caches or connecting to databases, the ALB health check may fail before the app is ready. ECS sees the ALB health check failure, assumes the task is unhealthy, stops it, and starts a new one, causing a continuous crash loop. Increasing the ECS health check grace period tells ECS to ignore ALB health check failures for a specified time after the task starts, giving the application time to initialize. Now let's rule out the other options. A. Decreasing the health check interval makes the ALB check more frequently, causing the task to fail health checks even faster. B. If the security group were blocking traffic, the original tasks would have failed as well. The problem started only when the new, slower starting image was deployed. C. The minimum healthy percent dictates how many tasks must remain running during a deployment. It does not prevent tasks from failing health checks. A helpful shortcut is this. If newly deployed ECS tasks are constantly being killed and replaced behind a load balancer, the container initialization time likely exceeds the ECS health check grace period. You have completed set 15 of the DOP-C02, AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.